Okay, good afternoon, everybody. So we will continue today the material on vibrations and how one can calculate them ab initio, and also what are the uses of this calculation. So I will consider a few examples as well. So just to remind you, one simple way of calculating vibrations is based on the frozen phonon approximation. And the idea here is that you displace an atom from its equilibrium position obtained using zero temperature calculation. And you calculate forces on all other atoms of the system. And this way, you can get access to a particular column or row of the force constant matrix, from which you can calculate vibration. So you displace one atom at a time, and you displace all atoms in the end. You get access to the whole square matrix of force constant matrix. And this one, after rescaling with atomic masses, would give you the dynamical matrix. Diagonalizing this matrix, you will get vibrations, eigenvectors, and squares of the frequencies as eigenvalues. We also discussed in some detail how this calculation can be done for solids, for crystalline materials with 3D periodic boundary conditions. And I explained to you that by taking an extended unit cell, you can obtain vibrational frequency for certain K points of the original crystal with a primitive unit cell. If these K points go into the gamma point associated with the reduced Brillouin zone of the extended direct lattice. So by taking different extensions from the primitive to the extended cells, you can get different reductions of the Brillouin zone from the original one associated with the primitive cell to the reduced one associated with the extended cell. And all the K points of the original Brillouin zone, which go into the gamma point of the reduced Brillouin zone, these are the points at which you can exactly determine the force constant matrix and therefore determine vibrations there. And of course, you're limited with this method because you can't take very large extensions. If you would like to calculate vibrations at K points, which are just slightly different from some particular ones, for example, around the gamma point, you would need to take very large extensions of the primitive cell with this method, which is in practice impossible. You can, of course, do some interpolation, but these are all very approximate. Okay, so that was the idea of this frozen phonon approximation method, and today we shall consider a number of different other methods which can be used to determine vibrations. And one method I wanted to start from is referred to as density functional perturbation theory method, DFPT. There's a lot of references to this method. This was initiated, as far as I remember, by Italian scientists. And the main advantage of that method is that it is based entirely on the primitive unit cell. Therefore, you have access to all K points. For each K point, you will have to run a calculation separately. But in principle, you have access to all K points using just the primitive unit cell. Of course, it becomes a very good practical method then, for example, for plotting phonon dispersion curves, when you have phonons as a function of the K vector in the Brillouin zone. I'm not going to go through this method in great detail, but I hope I will be able to explain you the main ideas of the method within the density functional theory. Okay, so what we need to know is a number of things from the density functional theory. I'm not going to explain this. I hope you had this covered at some point. If not, you will have to look this up. But we start from these Kohn-Sham equations, in which T is the kinetic energy operator, and G is the Kohn-Sham operator, which has the following form here. So it has the potential due to other electrons, the Hartree potential. It has a potential due to nuclei, and it has exchange correlation potential. And these orbitals here, these are Kohn-Sham orbitals, and these are Kohn-Sham energies. And the full electronic density is constructed from those Kohn-Sham orbitals by squaring them up and summing over all occupied states lambda. Okay. The Kohn-Sham potential can be actually obtained as so-called functional derivative of these three contributions to the total energy: Hartree contribution due to electron-electron attraction, exchange correlation contribution, and due to a term associated with the interaction of electrons with nuclei or atomic cores. All these terms depend on electronic density, and taking functional derivative of these terms, you determine the Kohn-Sham potential. So that's something I expect you either be familiar with, or you can look it up. The total energy of the system is written here. It contains this kinetic energy contribution and these energies I just mentioned. Apart from those three, you also have this energy here, which is the interaction between atomic cores or between nuclei, which of course does not depend on electronic density, but still depends on the atomic positions. And if we would like to calculate atomic forces, this is what we need to do to work out the force constant matrix at the end. We need to differentiate the energy with respect to atomic positions. Then, of course, that term is important. All right, we know from Hellman-Feynman theorem that the first derivative of the total energy with respect to atomic positions R, capital R, A here is the atom number, and alpha is the Cartesian component, x, y, z. So the first derivative of the energy with respect to atomic positions can be easily calculated. And what you need for that, only to know the Kohn-Sham orbitals. So you have a contribution from the electronic structure terms in the total energy here, where V is the potential due to interaction between electrons and nuclei. And you have this nuclear-nuclear interaction term contributing, which is just some function of the atomic positions. It doesn't depend on electronic density. But that term does. So if you write it down as the integral, you see you have it as that derivative of the potential integrated with the electronic density. So at that point, it's clear that atomic forces, which is just minus these derivatives, can actually be calculated, given that the Kohn-Sham problem is relaxed, is self-consistently converged, and you have access to Kohn-Sham states, electronic density. Therefore, you can work out these two terms very easily. And this is what any density functional code does for you when you finish your SCF cycles for the electronic structure. But in order to calculate vibrations, this is not enough. Of course, if we have access to the forces, we can calculate vibrations using the frozen-Phonon method. But this is precisely what we would like to avoid here, because we would like to get access to the force constant matrix, which is the Hessian of the energy with respect to atomic positions. So this Xi and Xi prime, these are my shorthand for the atomic positions, for the atomic positions and the Cartesian components. So we would like to do this, and to get the second derivative, you don't have anything like Hellman-Feynman theorem anymore. You have to really do the calculation explicitly. Yes, and with this method, this density functional perturbation theory allows you to do this calculation, but it's not as simple as just simply working out these contributions as given by the Hellman-Feynman theorem. You need to do a little bit more, and you have an additional SCF cycle involved here. Okay, so as I said, this would give you just a flavor of how this method works, just a general idea. So what we need to do now, considering this first derivative of the energy with respect to atomic positions, we need to differentiate it again with respect to Xi prime, another position, another atomic position, in order to get the full Hessian, the second order matrix of the energy with respect to atomic positions, which is the same as the force constant matrix. Okay, so this term would also contribute, of course, there was a second order term, but now we need to differentiate again this term. Of course, the potential experienced by electrons due to nuclei depends on the nuclear position. So we will have the second derivative of that potential, but that potential is just a Coulomb potential, or maybe it involves some local or non-local contributions as given by the pseudo potential. It is a function of the atomic positions, explicit function. It can be calculated. You need to integrate it with electronic density. In principle, this can be done. But electronic density also depends on atomic positions, as you would expect. You move atoms, electronic density changes. Therefore, we have to differentiate the density as well. And that's the main problem. That kind of contribution, when you calculated the first derivative, also existed, but it exactly cancels out. And this is the essence of the Hellman-Feynman theorem. When calculating the second order derivatives of the energy with respect to atomic position, this doesn't happen. So you need to have access to the change of the electronic density due to shift of atoms from their equilibrium positions. Yeah. So we need to work out how to calculate these derivatives. Then once we've done this, we can calculate the second order derivatives using that equation, and therefore rescale it with atomic masses, as I explained last time, and diagonalize, and we will get atomic vibrations. Okay. So when we change atomic positions, we need to solve the Kohn-Sham equation again, because the changing atomic positions would affect the Kohn-Sham potential. So let's now work out what is this change of the Kohn-Sham potential G due to the small change of some degree of freedom Xi, one atomic position. So that G is given by these three contributions. This one is just a pure Coulombic in a simple case of the core being just atomic core being just the nucleus. But if it is not, it's still a function of the atomic position. It doesn't depend on electronic density that term. So there will, but still it depends on atomic position. So there will be a certain change of that term due to the atom being shifted. However, these two other terms of the G operator, they do explicitly depend on the electronic density. So in order to work out the change of these two due to the shift of an atom, we will have to, first of all, account for the change of electronic density due to that shift of an atom. So this will look like an integral over the whole space. Then we take a functional derivative of these two terms with respect to electronic density times the electronic density change. So this is a chain rule, but applied with the mathematical tool of functional derivatives, because we would like to see what is the change of this potential due to the change of electronic density caused by the atomic displacement. This operator depends on electronic density in a very simple manner. It's just a Coulomb potential. So for this term, this functional derivative would give you just a pure Coulomb potential. Exchange correlation potential depends on electronic density in some non-trivial way. And therefore, the variation of that potential with respect to density would be a derivative of the potential with respect to the density, and at least in a local density approximation, LDA. If the exchange correlation potential depends also on the gradient of the density, it will be slightly more complicated, but we're just considering an idea. So this, again, given the certain density functional, can be easily calculated, and we have the change of electronic density. So atomic displacements causes a deformation of electronic density delta rho, and that in turn causes the change of the Concham potential. Once we have the change of the Concham potential, we can work out the change of the Concham orbitals and of the energies. So the derivative of that potential, Concham potential, with respect to atomic displacements, then will be given by the derivative of this nuclear electron interaction, and that term. In that term, of course, this derivative would go into derivative of the density. We will obtain this expression. So in order to work out this, and this would be needed to, if you like, update the Concham equations to get new orbitals, we need to calculate the change of the electronic density due to the shift of atomic position. Let's remind ourselves what the electronic density is in terms of the Concham orbitals. It's the sum of these orbitals squared over all occupied states. So if we would like to calculate the change of these orbitals, or the density due to the change of the orbitals, we arrive at that result. Yeah? So it would be orbital times orbital change, and then the second term, which is complex conjugate of the first. So the change of electronic density is related to the change of each orbital, and the change of each orbital is due to the fact that this Concham potential actually changes by this quantity delta G. And the change of the orbitals can be actually worked out using first order perturbation theory, and this is the result. In the first order perturbation theory, you get for the orbital lambda that linear combination over all orbitals, both occupied and unoccupied, vacant. With the matrix element of the change of the potential between orbitals of the non-perturbed system, which is when atoms are at equilibrium positions. Okay, so when you take this expression into here, you will find that, by the way, here we sum only over the occupied orbitals, right? But here we sum both over occupied and unoccupied orbital. By the way, this prime means you can look up the first order perturbation theory. If you don't remember this result, this prime means that lambda is not equal, lambda prime is not equal to lambda. We do not include the orbital lambda, which we are updating in the first order perturbation theory. And in fact, it makes sense because otherwise we'll have a singularity in the denominator. So I take this, substitute in here, and I will have delta rho. And by dividing this delta rho by the change of the atomic position, delta C prime, I would have that derivative in the end. So derivative of rho with respect to the C appears to be given by that expression, which contains the derivative of the Concham potential matrix elements with respect to that C. And in turn, that quantity, as we discussed above, is related to the derivative of the density with respect to this position. So we have a set of two equations you need to solve self-consistently. All right? But the important advantage of that method is that you do not need to go into extended unit cells. You can use the primitive unit cell for your crystal, And in fact, you can now then consider, in terms of these displacements, certain symmetry associated displacements associated with a particular K point in the billion zone. So you will have get access for any K point vibrations you like. And this is all done within the same framework. Okay, so this is density functional cell perturbation theory method, which allows calculating vibrations at any K point, and it is based on taking explicitly into account the change of electronic density due to atomic displacement. Of course, you have to go through the whole primitive cell, taking one displacement after the other to determine the corresponding displacement. But in principle, this can be done. These calculations are quite expensive, but they are exact. So this is yet another method. There are efficient implementations which take account of the symmetry of the system. And you can find them in Quantum Espresso, which was probably the very first quarter, maybe maybe one of the first where this was done, that in VASP and many others. So this is this density functional perturbation theory. What I'm going to do now is to consider something different. Again, it's to do with determining vibrational frequencies, but in a slightly different context, actually. We have discussed how the vibrational frequencies can be determined for crystalline systems. What about other types of systems? For example, liquids. In that case, it's a bit more complex, but still there is a way to do this by considering the following idea. Let's assume that for a short period of time, our system is kind of not frozen, but atoms vibrate around certain positions. So we would assume that there is some kind of equilibrium established over a short period of time, and around that equilibrium, our atoms vibrate. So it's like a crystalline system snapshot, and atoms vibrate. What I will show you that there is a very beautiful result actually existing, which can be applied to crystalline systems per se as well, of course, that density of states of the vibrations can be determined from the correlation functions of the molecule obtained through the molecular dynamic simulations. So this is yet another method of determining vibrations. So in order to discuss this, again, this will be done rather quickly, just to give you an idea. Of course, you will have to study this if you want to do this properly yourselves with the original literature. But the idea of the method is shown on that on a couple of slides. So first of all, let's start from the Hamiltonian or classical Hamiltonian of our system. So kinetic energy and the harmonic potential energy. So phi here is a force constant matrix, and U are atomic displacements, P is the momentum. The Lagrangian of the system is kinetic energy minus potential energy. Okay, and we will need both of these. We know from the lecture last week that the potential energy can be diagonalized and presented in that form where we sum over all normal modes, eigenvectors of the dynamical matrix. So this is the eigenvalue and eigenvector problem for the dynamical matrix. And these normal modes can be written via atomic displacements U in this way. So Y, capital Y here, are eigenvectors of the vibrations. You can also consider velocities associated with the displacements by simply differentiating with respect to time this line. You arrive here, and then you can solve this equation with respect to velocities of atomic displacements. This is done by simply multiplying both sides of this expression by J component of the normal mode and summing over all normal modes. And if you do this, you would be able to determine what is the atomic displacement velocity in terms of the velocities of normal modes. Okay, and that we need because what we would like to do is to calculate the kinetic energy. Kinetic energy is originally given by the velocities of atomic displacements. But now if we substitute this expression here and perform a little algebra in particular, using the fact the eigenvectors of the atomic vibrations, these ones here, are orthogonal to each other, we will obtain that in terms of the velocities associated with the normal modes, kinetic energy is also diagonalized. So this should not be a surprise. We discussed that by going into the normal modes, we diagonalize the whole Hamiltonian. So this is just that. We just perform a diagonalization of the potential energy and the correspondingly kinetic energy. But what we will like to do next is to assign to these velocities of the normal modes lambda, y lambda dot, momenta, conjugate to the normal modes y lambda. Okay, and this is done if you recall classical mechanics by differentiating Lagrangian with respect to normal modes velocities, which I call Q here, but in fact these are these guys here. And if you perform that calculation, so you need to differentiate only that term because the potential energy just doesn't depend on the velocities, you of course obtain y lambda dot, which we know is related to displacement velocities u dot using that formula. And therefore, our normal modes, this momenta, are related to the velocities of the actual displacement using that formula. And since momenta of displacements are simply mass times velocity, we can finally write down the relationship between the atomic momenta and normal modes momenta. All right. And this way we can write down finally the kinetic energy. So the kinetic energy, so this momenta are just simply y lambda dot, yes, as I explained. So kinetic energy and potential energy sum up together, and we have for the total Hamiltonian of our system, that expression, and this is nothing but a sum of independent harmonic oscillators. So you can recognize in this a harmonic oscillator Hamiltonian, kinetic energy with a mass equal 1 and the potential energy, which we will use a small h to denote them. Okay. So let's summarize what we've got so far. So we have the Hamiltonian in the harmonic approximation of our system, which can be written via normal modes as the kinetic energy and potential energy for a single harmonic oscillator. And when we sum over all normal modes, all these harmonic oscillators are independent of each other. We can also write down a relationship between normal modes, positions, and momenta, and atomic positions and momenta, okay, using these linear transformations. We also know, we did it last time, that these normal modes, they satisfy single harmonic oscillator equation, which again, not a surprise because each normal mode y lambda is governed by this simple harmonic oscillator Hamiltonian. So you would expect an equation of motion like this. And solving this equation of motion, you obtain an explicit classical function of how this normal mode depends on time. What you do not know is this constant a lambda and a complex conjugate term, a lambda complex conjugate, because these are to be determined from the initial conditions. Okay. we would not know initial conditions for the atomic velocities and momenta in terms of normal mode, but we would know them for actual atomic displacement. So what we need to do now is to solve these two equations with respect to atomic displacements and momenta, and these relationships are written here. So this is for the displacement, as they depend on the y lambda normal mode displacements, and therefore explicitly given as a function of time. And the same expression can be written for the momenta. And then, given at time equals 0, t equals 0, we know the positions and momenta. We can solve these equations at time equals 0 with respect to this constant a lambda, which is a complex constant. And if you perform this calculation, you will obtain for a lambda this explicit expression. It depends on atomic positions and momenta at time equals 0, substituted back into this equations here, and you obtain this boxed equation for the atomic positions and momenta of our classical vibrating system. This is basically what we have just done. Is we solved equations of motion for our vibrating system explicitly, and moreover we used initial conditions and written the whole solution subject to the initial conditions. So these blue guys here, these are initial positions and velocities. You may ask why we need all this. Okay, so this will become clear from this slide. Because what we would like to do now is to calculate correlations functions of these momenta, okay, at different times. So we would like to calculate something like that. This is the object we would like to calculate. So that is why we need explicit expressions for the momenta for each degree of freedom I as it changes with time. And now we have this expression here given explicitly. But we need to somehow, oh, here, I actually written it here. But we need also to account for the fact that when the system is prepared initially, we actually do not know explicitly what are initial positions and momenta. So we need to use statistical mechanics here. We need to assume that these initial positions and momenta are governed by a Gibson distribution with the Hamiltonian, which we worked out like this, sum of simple harmonic oscillators. So if we would like to calculate any observable quantity, and this is one of these possibilities, it's an observable quantity, we would need to statistically average it with respect to all possible preparations of the system at the 0 time, okay? So we need to assume that with respect to initial positions and momenta, our system is governed by the Gibson distribution. And therefore, that is the distribution here. Yeah. So we have exponential minus beta. Beta is inverse temperature. H is our Hamiltonian at the initial time, but Hamiltonian doesn't change as the time evolves in this approximation. Z is the statistical sum. Yes, and if we would like to calculate an average of some quantity, which is an explicit function of the degree of the normal mode lambda, we would need to calculate this integral by integrating over the whole phase space of our system, all displacements and all momenta. Okay. So that's the idea. In order to calculate this correlation function, we actually integrate over the phase space with respect to the Gibson distribution associated with the initial preparation of our system. So how can we do this in practice? First of all, it's rather difficult to perform the calculation using explicitly initial positions and momenta. It would be more convenient to exploit the fact that the Hamiltonian splits up into non-interacting Hamiltonians of each harmonic oscillator. Therefore, we will change our integration variables from U and P into Y lambda and P lambda. And this can be done using a Jacobian, and Jacobian can be easily calculated to be shown equal to 1. in that case. And then if we would like to calculate something like that, an average of this kind, where f lambda is some function of the degrees of freedom of the normal mode lambda, then this exponential function, because the Hamiltonian is a sum of the Hamiltonian, this Hamiltonians for each harmonic oscillator, this exponential function becomes a product of exponential functions associated with each normal mode lambda prime. So it's a product of these exponentials. The same can be said about the partition function. It will also be a product of partition functions. So in these new variables of normal modes, we arrive at this. And if f depends only on particular lambda, then integration here over all other lambdas not equal to lambda would simply cancel out with z, because it is z, and we are left only with the integral associated with the normal mode lambda. So we will arrive at that expression. Okay, by the way, that z lambda, the partition function due to a single harmonic oscillator, is easily calculated. It is equal to this. Now, equipped by these simple results, we can work out different averages. First of all, let's start from average normal mode displacement and momentum displacement, because the functions here contains the Hamiltonian, which is a quadratic with respect to atomic displacements and momenta. These are just Gaussian integrals, and of course, when you calculate average of these guys, you will simply get 0. Because the Gaussian centered at 0. The same is true for this product of y lambda and p lambda, for any lambda in lambda prime. However, when you calculate the average like this, y lambda and y lambda prime, if lambda and lambda primes are different, of course, you would simply have a product of two averages for lambda and lambda prime, which would give you 0. However, if lambda and lambda prime are not different, you will have y lambda squared here, and then using that result for y lambda squared instead of f lambda integrated, you will obtain this. Similarly, for the momentum, it's also diagonal, and you will have 1 over beta when lambda is equal to lambda prime. So the bottom line here is that we can calculate averages we need for the initial preparation of our system using statistical mechanics. And therefore, we can now calculate these averages with respect to atomic positions, atomic displacements, and momenta, using our original indices I and J, which numerate atoms and their Cartesian coordinates, degrees of freedom. And if you do this, first of all, you would use a relationship between this and the normal modes, which I gave you here. And this would be, of course, related to the averages with respect to the normal modes at initial time, which we have just calculated, and you will have these results. And that average is equal to 0. So at that point, we managed to calculate the correlation functions at 0 time for all our positions and momenta. And now we should be able to calculate the correlation function we're really after at time t and t prime. So in order to do this, I need to take this expression for time t and a similar expression for time t prime, multiply them together, and once you multiply, take the average. And when you take the average, you will have a product of two displacements with each other, two momenta with each other, and a two hybrid term, u multiplying p and p multiplying u. Yes, and if you do the calculation, it's a bit bulky, but in principle simple, and using the just obtained expressions for these averages, you can work out that that correlation function is actually equal this 1 over beta and sum over all normal modes of cosine functions for each vibration. And if you now take the Fourier transform of both these sides, you will obtain that on the right-hand side, you have a sum over delta function, omega square minus omega lambda square, summed over all all normal modes. So this is actually phonon density of states. So what does it actually mean? It means that if you calculate a certain correlation function, momentum correlation function of your system using molecular dynamics, means you have access to the density of states or vibrational density of state of your system. And here you have an example of such a calculation of water. And you can see that there are some peaks in this density of states associated with two vibrational modes of the water molecule. So there is a way to access vibrational properties of liquids using molecular dynamic means. So far our consideration was classical. By the way, if there are any questions, does anybody want, because I'm going to somewhat different topic, to ask any questions about the material so far? Okay, let's assume that all is crystal clear. Let's move on then, yeah? So now quantum consideration. So far we did classical. Our consideration was entirely classical. But if we would like to approach the problem quantum mechanically, what we need to do, we again start from the potential energy, which is a quadratic form with respect to atomic displacements, but this time within again within the harmonic approximation. But this time we would, instead of solving classical equations of motion, we would solve the Schrödinger equation. So this is the kinetic energy, and this is the potential energy of our system. The solution of this rather complicated at first sight Schrödinger equation can be done rather easily by going into normal modes. So what we need to do, we need to make a linear transformation of our displacement u into normal mode y lambda, as we did before. This results in the potential energy being diagonalized with respect to new coordinates y lambda. This is exactly what we did before classically, and this is that transformation written again. The momentum which appears here associated with degree of freedom I is of course given by the quantum mechanical expression like this, where we have this derivative with respect to atomic displacement. But atomic displacements are related to displacement of the normal modes. Why this linear transformation? So this derivative can actually be calculated using the chain rule, and we can associate the momentum, normal mode momentum, with this minus IH bar and that derivative with respect to the normal mode. So this would give us a relationship between the momentum operator with respect to in usual representation and the normal mode representation. And similarly to what we did with the kinetic energy in the classical case, we can work out what is the kinetic energy operator would be now in terms of these p lambda quantities, and it appears to be exactly the same as in the classical case. So you should be able to see here full analogy with the classical case. So the Hamiltonian again is a sum of independent Hamiltonians, each associated with a single harmonic oscillator with frequency omega lambda and unit mass. And since we know how to solve the Schrödinger equation for a single harmonic oscillator, we get the energy like this, where these numbers n lambda take on values 1, 0, 1, 2, 3 up to infinity. But because and the wave function is given by that, it's related. I just remind you, there's an exponential term, and the Hermite polynomials in that function. But because the Hamiltonian is the sum of the Hamiltonians, it's known from quantum mechanics that the energy is the sum of the energies associated with each of these single Hamiltonians, and the wave function is a product of the wave function. So in principle, what that means that in the harmonic approximation, we can actually exactly solve for the vibrational problem and determine eigenstates of that set of harmonic oscillators. We can, of course, we can use coordinate representation, and these wave functions, as I said, these are related to Hermite polynomials multiplied with exponentials. But it's actually convenient to use a slightly different representation in which we indicate the excitation number n lambda, which enters this energy expression. And this is what I will use. Then the Hamiltonian is essentially, this is a second quantization, but I will use it just here and just for a single purpose, to be able to write the Hamiltonian of each harmonic oscillator in that form, where this n lambda is an operator which, when acted on the wave function, would give me simply the occupation number. That's all I need. I won't use this expression. So if you are not familiar with the second quantization, that's not really a problem. What we're going to do now is to calculate the Helmholtz free energy of our system of harmonic oscillators. The Helmholtz free energy, which is U minus Ts, T is temperature, S entropy, U internal energy, can be related to the partition sum Z using this formula. And what is the partition sum or statistical sum? Is a trace of that exponential operator, where beta is the inverse temperature and H is the full Hamiltonian of our system. And because our Hamiltonian is the sum of the Hamiltonians associated with each harmonic oscillator, which and the harmonic oscillators are independent, that exponential operator becomes a product of exponential operators associated with each single oscillator, and the partition sum becomes a product of partition sums over all normal modes, and this is the partition sum due to a single harmonic oscillator, and that can be easily calculated. So the calculation goes as follows. So if we consider the trace of that operator, we basically sum over all possible wave functions of that operator, of that operator H, and we take a matrix element of that exponential operator. So all possible wave functions of our harmonic oscillator are numbered by these numbers n lambda, the occupation numbers, and they change from 0 to infinity. So we need to just sum that expression from 0 to infinity. When I act with this operator on this wave function corresponding to the occupation number n lambda, what I simply do, I replace this operator with its eigenvalue. So basically, I replace this operator n lambda with the value n lambda. Yeah. So this is what I've done. So that whole matrix element becomes now just this exponential, with n lambda being that summation index. This is the geometrical progression which can be calculated. This is the result. And now, if you calculate the free energy, you need to take a logarithm of a product of this for different lambdas, and you obtain that result. And after simple algebra, you obtain this expression. So what is this? This is the free energy contribution, contribution to the free energy due to atomic vibrations. And each oscillator contributes that much. So there's a 0 point energy, H omega over 2, and there is some term which depends on temperature. Yeah, so the free energy, it depends on temperature. So now we will try to use this result for studying thermodynamics of crystals. You know that that if we work within the harmonic approximation, our potential energy surface is harmonic, and therefore, if you increase the temperature, atoms vibrate still symmetrically with respect to the equilibrium position at 0 temperature, and there will be no thermal expansion. In order to include thermal expansion into consideration, and we will have to do this if we would like to consider thermodynamics, we need to take account of the harmonicity. So additional terms in the Hamiltonian, which contain cubic, fourth power, and so on, all the terms with respect to atomic displacement. So far, in the harmonic approximation, we only used quadratic terms. Once we use these higher order terms, the potential energy is not longer symmetric with respect to equilibrium at zero temperature. And therefore, when atoms start vibrating, they're going towards higher displacements more often as the temperature is increased. And that results in the shift of this average position to the towards the thermal expansion. But this type of calculation is rather complicated. If you want to use these explicitly anharmonic terms, you will need to calculate the third order, fourth order derivatives of the potential energy, of the total energy of the system with respect to atomic displacement. You have seen that the second order derivatives are rather complicated to calculate, and let alone third and fourth order. So there is a way to avoid this calculation of higher order derivatives of the energy and perform a calculation in so-called quasi-harmonic approximation. How does it work? When we relax a structure at zero temperature, we will obtain lattice constants or obtain a crystal volume. So there will be a volume of the primitive unit cell of our system, or maybe conventional unit cell, whatever unit cell you are using. But you can also take an arbitrary volume of your system. For example, if you have a cubic crystal, you will just take another lattice constant, which is bigger than the one at zero temperature. And in that case, of that other expanded unit cell, you can also relax atomic positions, obtain your DFT energy, and also obtain vibrations. So if you then add to the DFT energy that vibrational energy we obtained for the harmonic oscillations, this vibrational energy would also depend on the volume at which you calculated it. But it also would depend on temperature. So this way, if you sum up these two contributions, you will obtain free energy as a function of the atomic or of the volume of your crystal and the temperature. If you now minimize this free energy with respect to the volume, so we will perform this calculation for a set of volumes. For each temperature, you will obtain the minimum at different volumes. And this would give you an equation of states of your system. You will be able to consider expansion. If you like to consider full thermodynamics of your crystal for non-zero pressure, so this was a zero pressure consideration, then instead of Helmholtz free energy, you have to use Gibbs free energy, which has this extra term PV. And in that case, minimization of the Gibbs free energy would give you this equation of state. So that derivative, instead of being equal to zero, would be equal to minus pressure. And this way, you will obtain the equilibrium volume for the given temperature and pressure. So that's basically the idea. And before discussing advantages and disadvantages of this kind of calculation, let's consider a few examples, all right? And then I will present another method which can also be useful in that regard. But let's look at the example. So here, I have one study which we did some years ago on certain molecules which are shown here on the calcite surface. So these molecules, when deposited on a calcite surface, I won't be going through the whole story. This would take a bit of time. If somebody is interested, there is a reference here at the bottom. So when you deposit these molecules on the surface, they first form a so-called step network. Here you can see the step network, which consists of, stripe network, which consists of stripes of dimers. Some dimers are stand up, some dimers are horizontal. There's a side view from one angle, side view from another angle. However, when you heat the surface, these striped networks develop into a different structure, which we called dense network, in which the molecules are all standing up vertically at some angle, but basically vertically on the surface. So what we did in this study, we wanted to understand whether there is kind of a phase transition, at which temperature it happens. It appears to be not so trivial, but we were able to work out for each particular structure, calculate phonons associated with the molecule and some contribution from the upper surface layers. And using this expression for the vibrational free energy, we were able to plot the dependence on temperature of the free energy in both structures, which are shown by these green and blue lines. We also worked out the free energy, how it changes with temperature for the molecular gas. Because initially, when the temperature, when the molecules are adsorbed on the surface, and before they actually find each other and form a monolayer, they move on the surface rather freely and form a gas. So we considered two types of gas: gas of dimers and the gas of monomers. And in these cases, we needed to add to the free energy, which I considered so far, also the configurational entropy contribution, because you can arrange these molecules on the lattice in different ways, and you have to take account of this effect as well. So if there are m sites on the surface and n molecules, you can arrange this that many times, and this would make a contribution to the configurational entropy. So, and the result can be actually written in then via the coverage, number of molecules per number of sites, both for monomers and dimers. And here you can see two other curves showing monomers and dimers. And there was a very interesting question as to why monomers free energy is the lowest of all. But initially, when the system is prepared and the molecules are evaporated from a chamber onto the AFM chamber where these pictures were taken, why is it that initially they form dimer gas, and which dimer gas goes into the striped network of dimers, and only after some heating up we see the dense network of standing up monomers, but we never actually see monomers as a gas. But that's a different question I'm not going into. Here you can see another example, a rather old example. I think there's a reference to 2001 from an Italian group of a phase transition from FCC diamond structure of tin, so-called alpha tin, to the body-centered tetragonal structure of tin at higher temperatures. The transition happens at 13 degrees centigrade. What they did in that paper, I call it naive quasi-harmonic approximation, because they didn't determine as a function of temperature the volume of that crystal. They used phonons calculated at zero temperature. So they simply took zero temperature phonons, and that would give them a contribution to the free energy as a function of temperature only. Still, when they looked at the total free energy, they plotted the free energy as a function of temperature. They got a crossing here in the free energy. So at low temperatures before that temperature here, this is experimental temperature, 13 degrees centigrade, they got the alpha phase lower free energy than the beta phase as experiment predicted. But after that temperature, the beta phase wins. They also looked at the density of states of phonons, and you can see that alpha phonons have high frequency phonons, but beta phonons do not. And they use this fact to explain what actually played the dominant role in establishing the free energy at lower temperatures of the alpha phase being dominant, why the alpha phase wins. So this is naive quasi-harmonic approximation because they didn't take account of the volume change of the crystal due to no, they did take account of the volume change due to DFT calculations because they considered different volumes, but they didn't take account of the phonons frequencies change due to that volume. There were, however, in that paper here, people actually did this. This is the full quasi-harmonic approximation approach. So what they done, they considered a number of simple metals. These are all cubic structures. So the volume is basically measured by the lattice constant of these crystals. So it's very easy. You change the lattice constant and you change the volume. And then you can calculate for different crystal volumes, you can calculate the density functional energy using a very good K-point sampling. You can also calculate phonons. I think they didn't use in this paper perturbation theory. They used frozen phonon. That's why they had to go to very large supercells to get access to many K points of phonon modes to estimate the quasi-harmonic contribution of the vibrations into the free energy well. They also did add anharmonic contributions and a contribution due to free energy due to defects, but this is not the point. But so they done all this very, very thoroughly. It's a big paper. I remember I was quite impressed when I read this for the first time at the work they done. So this is what they did here, written here. So they determined for various volumes phonons, they determined DFT energy, therefore frequencies, and then they even interpolated the frequencies between the K points they had access to due to this particular supercell they have used. And in the end, they solved the equation of state for the crystals to determine the structure as a function of both pressure and temperature. A very, very detailed study. So here you can see some of the phonon modes they obtain for these systems. Only acoustic modes here because just one atom in the primitive unit cell. And here you can see expansion of those crystals in comparison with experiment, which is quite impressive. Of course, this calculation is rather substantial, I would say, yes, if you want to really push towards high precision. But there is another problem with this calculation. It can only be done really for cubic systems. Because if the crystal is not cubic, how would you do this? So suppose you have some hexagonal structure. You have a few parameters there you have to change. So if you even consider that the structure we looked at, the body-centered tetragonal structure, it has I believe 2 or 3, I can't remember, this lattice constants you need to take account of. So if you have a cubic structure, you have just a single variable to change and to determine DFT energy, to determine vibrations. But what if you need to specify your unit cell with more than one parameter? Then for each combination of these parameters, you will have to do this calculation. It becomes really, really difficult. Yes. So you have your free energy not as a function of a volume. We have a free energy as a function of as many parameters as needed, up to 6 in a general, in the least symmetric primitive cell possible. Up to 6 parameters, you have to investigate how phonons change, how the density, how the energy changes, density functional energy changes as a function of all these parameters. These calculations become really impossible to do. So what are the methods? So let's just have a look again at the situation. So we have DFT plus quasi-harmonic approximation, which gives access to the free energy via this quasi-harmonic expression of the free energy due to vibrations, as we discussed so far. But this method is, as I explained to you, practical only for cubic systems. It's difficult in this method, possible but difficult to include anharmonicity, and it fails near phase transitions, and also in some other cases when you have unstable structures for which vibrations cannot be determined. So basically, you need to know what the structure is beforehand to determine vibrations there. That information may not be available. There are some other methods. So this self-consistent phonon method, which I do not consider, it's very difficult to implement in practice. In fact, I do not know any implementation. As we discussed, there is a velocity autocorrelation function method, which works for finite temperatures, but you need to run molecular dynamics, and therefore ab initio this is a little bit difficult. Although this method takes account of anharmonicity, because everything moves, and you're not, and you will have peaks in the density of states, not only due to harmonic phonons, but they will be slightly smeared out because of the harmonicity. You can improve on that method using thermodynamic integration, but again, this is rather complex method, which requires a lot of compute resources. And yet there is one more method which may be more appropriate for a general crystal with a structure which is not quite as simple as the cubic structure. So here are a few references to this method, and I will try to explain to you the main ideas of this method. It's called temperature-dependent effective potential method. It is also based on molecular dynamic simulations, but it doesn't assume a particular crystal structure. So you obtain a crystal structure during the course of application of that method. It can work at different pressures, at different temperatures, includes anharmonicity, and basically, as I said, can be extended to any type of crystal lattice. Okay, so what are the main ideas of this method? Just one slide. Suppose you would be able to run, for the given temperature and pressure, molecular dynamic simulation in the NPT ensemble. You would then determine, by averaging your results after the equilibration of the system, what is your crystal lattice is, what is your unit cell, what are the lattice parameters, and where atoms are in that lattice on average. Okay, but what you really want is to calculate the phonons. So you would like to then assume that the structure you obtained, this is an average structure, but atoms are actually oscillating around these average positions, and you would assume that the potential energy of your system would be given by the potential energy at that temperature, at these conditions, when the atoms are at these thermodynamic equilibrium positions. Plus, there's a quadratic term with respect to atomic displacements. And here you have a matrix phi, force constant matrix, associated with this particular structure. If we knew this force constant matrix, we would be able to diagonalize it. In fact, not this matrix, but rescale with atomic masses, and therefore determine the dynamical matrix and diagonalize it, as I explained before. And that way you would obtain the phonons. But how to get access to this matrix? How to determine this matrix? So that's the main idea here. What was suggested? So you run a molecular dynamic simulation NPT first to determine the structure on average. Once this structure is known, you fix the structure and you run NVT simulations. All right. So you keep the volume, you keep the shape of your unit cell, constant, and you run NVT simulation next at a given temperature. Once you run these simulations, atoms would oscillate around their thermodynamic equilibrium positions, and at each of such set of atomic displacements, you would get atomic forces acting on atoms. So you will have, during the course of your molecular dynamic simulation, a large number, depending on how many molecular dynamic steps you would take, a large number of vectors of atomic displacements, U, and the vectors of atomic forces, F. And for each of those steps of molecular dynamics, you would imagine that there must be some linear relationship between the forces and atomic displacements. And that linear relationship is established on average by this matrix phi of force constant matrix. But there is a problem. Of course, for each particular molecular dynamic step, we have this relationship. But but we have much more information than just one step. We have maybe thousands molecular dynamic steps. And for all of this, we have these forces and displacements. On the other hand, that matrix is small. It's a square matrix of the size of the number of degrees of freedom of our crystal. So we have a huge vector of atomic forces. If we combine all the forces for all atomic steps, or molecular dynamic steps, we have huge vector of atomic displacements, but a little matrix of the force constants. So the idea is to determine this best matrix such that would minimize, using least square error function, that expression. So what we have in this expression, here you have actual forces on atoms at each molecular dynamic step, and you sum over all molecular dynamic steps, all times. Here you have atomic displacements at this at each step, molecular dynamic step t. And here you have the unknown matrix phi. So that product of phi and u would give you expected force. And you would like to fit that phi such that the difference of these predicted forces, if you like, and actually observed forces phi, F in the molecular dynamics squared, would be minimum. This is over defined problem, because we have much more data than the number of unknowns we would like to determine. This matrix F is symmetric, and you have n times n plus 1 over 2 unknowns, the number of elements along its diagonal, and one triangle, rather upper or lower triangle of the matrix, because it's symmetric matrix. So we have a rather small number of values to determine, but a very large number of this kind of relationships. Okay, so mathematically, this is a known problem. It's called pseudo-inverse. With Moore and Penrose established this some 50 or 60 years ago, maybe even more. So there are routines which allow you to determine the best matrix phi given the long vector F of forces and the long vector U of displacements. What these people in these papers actually suggested is to determine the best force constant matrix out of the molecular dynamics run, NVT molecular dynamics run. And once you have this matrix, you can determine vibrations. And here you have an example of BCC lithium dispersion curves of the vibrations. So if you calculate vibrations at 0 temperature, you just relax your lithium and then you determine vibrations. You will find that some of the vibrations have imaginary frequencies. So omega square is negative. Yeah, remember, omega square is the eigenvalue of of dynamical dynamical matrix eigen problem, and dynamical matrix is symmetric, so we're guaranteed that the eigenvalue is real, so omega square is real. We, however, are not guaranteed that it's necessarily positive. So if omega square is negative, that means that omega is purely imaginary, and that corresponds to an instability in the system. The system would not like to stay in that equilibrium position. When you displace atoms, the energy is reduced. So this is not a minimum; it's rather a saddle point. So if you perform a calculation for the structure which is minimized at zero temperature, the vibrations are not contain imaginary frequencies, and this is what is shown here. However, if you perform this procedure properly by accounting for the thermal expansion of the system, then at 300 K, so this is the red curve, 300 K, you have a very good agreement with the experiment. So this time the structure is different, but so if you able to determine the structure, you can determine formulas for the structure, and that's what you get in experiment, because experiments are not conducted at zero temperature; they are conducted at some particular temperature. And here you have by symbols, you have phonons for 300 K, and the calculation shows a rather good agreement with experiment, and most importantly, no imaginary frequencies. On the right, you have zirconium, a different example, where there is a lot of imaginary frequencies at zero temperature. However, at 1300 K, you have a rather good agreement with experiment. Okay. So what we have done so far, we looked at a rather different methods which could be used to determine vibrational spectrum of the system. They range from classical force methods, when you start from some classical expression for the system energy as a function of atomic distances, angles, etc., as we did for the water molecule, for instance. And this way you solve the vibrational problem, you determine frequencies. Then you can do this ab initio, again assuming vibrations are classical, or using this method I've just considered, or molecular dynamics to determine the density of states. But let's now consider another application, an application of that method, specifically for determining transition rates. So this is a very important problem if you study kinetics. How when one structure goes into the other, for example, due to temperature, some thermal transformation of the system. What are the rates? It's very important to be able to determine those. So apparently, the rates can be determined if you have access to the energies of the system and its vibrations. So what I'm going to consider now is it's called transition state theory. Again, just few brush strokes basically on this, and specifically at the end we will consider vineyard theory, which gives an explicit expression for the transition rate for a multidimensional system going from one potential energy basin into the other potential energy basin via minimum energy path, which involves knowing vibrations. So that's why I included that example, because vibrations are here as well, and this is just another application of the vibrations. Okay, so let's start from that simple example of a one-dimensional system first, just to understand what is going on. So, so we have a single coordinate x, And my system, for example, it could be molecule AB, and we're considering distillation of that molecule into part A and part B. My molecule AB sits here at a value of x naught. This is its potential energy minimum. And this is the potential energy of my molecule as the x changes, the distance between atoms changing. And at some point here, my molecule, if I stretch it that way and release, it will go to infinity. These two parts go to infinity without any additional effort. So they will never go back. Yes, if you expand it up to that point, they will go back and would still be a molecule AB. But if you stretch it too much, you will break the bond, and you will have these two A and B separate. So the energy here reaches maximum, and then the energy goes back to goes down again. So this would be the energy barrier for the dissociation of that molecule. Let's try to work out what is the transition rate from here to here. Okay, so this is my Hamiltonian for my system, single degree of freedom, just one kind of atom, if you like, kinetic energy, potential energy, that potential energy which is shown here. We can consider the probability for my atoms to be at a particular momentum P and the separation X by this Gibson distribution. So we do have Maxwellian part depending on velocities, just a usual one, and would have some part associated with the potential energy. And the potential energy would have its own contribution to the partition function, which is just this integrated exponent. And I integrate only within the basin of the initial state. I don't integrate up to infinity because my potential energy doesn't go like this. It has changed its shape. So I will integrate only up to here. Then the rate of transition can be determined in the following way. First of all, we will calculate the probability to find my system at that point. And that would be given by this potential part in the probability exactly at the x equal xb when I reach this maximum here. On the other hand, it is not enough just to reach this point. You need to have your velocity being directed to the right, because if the velocity is directed to the left, the system would return back to the basin. So I would need to consider also the probability for my system to have a certain velocity v, and I would multiply by v to have the flux, and integrate only all velocities which are directed to the right. So from 0 to infinity. I don't consider velocities from minus infinity to 0. Only velocities directed to the right. So this integration can be easily performed. First of all, this part doesn't depend on the velocity, can be taken out, and the rest of it would give me some average velocity to the right, which again with the Maxwellian distribution can be worked out very easily. Then that potential energy part, I may assume that this part of the potential energy surface is harmonic with some frequency omega naught. So I can estimate it as a sum of the energy at the minimum plus some quadratic term with that frequency omega naught. And then I can use this expression to perform calculation of the partition function, which I still need for that probability P at the transition point. When performing this calculation, of course, I can expand the integration from minus and plus infinity, because my exponential term here would decay so quickly at this value. So there's no point of keeping any more 0 and xb here. And that calculation is performed, and we'll get this result. So putting everything together now, we will arrive at that expression. So first of all, from the velocity, I get this. From the partition function zx, I will get inversed that expression. But that expression Yeah, that expression from the partition function, yeah. And this is that exponent here. I need to calculate at xb at that point. But what we find that these two exponents actually combine into one, in which I have a difference of the energy at that point and energy at the minimum. Yeah, so that potential barrier. So what we arrived at is the transition rate is exponentially depends on the energy barrier delta, that quantity here. And it has a prefactor, this prefactor, which if you cancel out whatever you can, beta can be canceled out, the masses can be canceled out, you get this. What is this? This is a rate with which my system oscillates in this energy minimum. So omega naught is the frequency, but omega naught divided by 2 pi is the rate with which it oscillates. So, all right, so this is 1 over the period of oscillation. So basically, this expression can be interpreted in the following way. The transition probability for a single attempt is proportional to this exponent. The larger the barrier, the lower the probability. The larger the temperature, the smaller beta. Again, the larger the probability. But the system per unit time makes that many attempts to actually cross the barrier. So it oscillates, and at each attempt, with that probability, it has a possibility to cross the barrier. And it makes that many attempts given by the frequency of oscillation in the basin. Okay, so that's the idea of this result. Of course, this is a very simple result, which only valid for one-dimensional system. Question you may ask is whether it's possible to just generalize this to a general multidimensional system. How to determine the transition rate then? So I have a few slides. Again, if somebody is interested, I have a more detailed, full derivation of that, which is probably available on the TYC website anyway. It was some time ago. But I will just explain you a few important points here. So on the left, we have that very, very general system. So we have two basins on the potential energy surface. That's the reactant basin, the initial state, and that's the product basin, the final state. So these circles, they mean the potential energy surface. So this is the minimum, and then with each new circle, the energy goes up. Yes, so I can't obviously draw this, but this axis is meant to be out of the plane or of the screen. Yes, and the same for the product basin. And we also can introduce so-called dividing surface. Surface which goes between these two basins and which has a minimum at a certain point here. And in both directions out of that minimum, the energy is increasing. The energy, however, is decreasing if we go towards the basins in the direction perpendicular to the dividing surface. So that dividing surface is actually a saddle. Yeah. So the energy from at that point is a minimum if you go along the dividing surface, but it's a maximum if you go across it between two bases. Then we can introduce a function f, which is a function of all all degrees of freedom q, which are relevant for our system. So I use q. Q could be many. And we will make that function, we will choose this function in the following way. We will make it negative at the reactant basins, positive at the product basins, and equal to 0 exactly when we are on the dividing surface. Moreover, we shall choose this function such that if you calculate the derivative of that function on the dividing surface, but in the direction perpendicular to it, that derivative will be equal to 1. So this is basically the gradient. All right. What we're interested in is in calculating the rate with which my system, which sits here in this reactant basin, may cross the dividing surface and go into the product basin. We would like to calculate the rate of transition. And of course, I will assume that my system sits here in the reactant basin by Gibbs distribution, as we did with the one-dimensional case. And then we would like to calculate the rate of transition of my system through the dividing surface. The rate of transition can be given by this expression. So V is this velocity of my system, is a vector, multi-dimensional vector, and N is the normal to the dividing surface at a particular point. So dividing surface is big, and at each point we have normals. So this, you may have seen this expression before when you do kinetics. You always come across this kind of types of expressions. What is the number of transitions one can make through a surface area ds per unit time? This is what this is actually. So if we would like to calculate, yes, and the normal is determined by the gradient of my function f I just introduced to you. So the total flux per time delta t through the whole, due to the whole dividing surface, is of course obtained by integration. So first of all, we're integrating over all dividing surface. So we allow transitions through all points of the dividing surface. Yeah. And also we integrate over all possible velocities, but we have to be careful with the velocities, because remember, in the one-dimensional case, we were considering velocities directed to the right only. We were integrating from 0 to infinity. Here we do the same. We take only those velocities when we integrate over velocities which are making an angle less than 90 degrees with the normal to the surface. So only those velocities which are directed from the reactant basins into the product basins. So that's why we have this Heaviside function. If these two vectors v and the gradient or the dividing surface function, if this dot product is negative, then this Heaviside function is 0. So we would exclude this. How this is done in practice, this calculation, we will see in a second. But this is just our derivation for now. Then this dot product, it comes from here. And that is the probability to find my system at the point QS on the dividing surface, that coordinate QS, with the velocity v. So it's basically that expression is exactly the same as this one for the one-dimensional system, but generalized to many dimensions. That probability contains the it's a Gibbsian probability, so it contains the exponent with the full Hamiltonian and the partition function. And the partition function is the integral over the whole phase space, all coordinates and all velocities. And we only integrate over reactant basin, as we did before. Remember, before we integrated over the reactant basin, we integrated here. So we do the same here. We integrate over the reactant basin when this function f we introduced is negative. So minus f is positive. Of course, the integration over the dividing surface can be extended to the integration over the whole space by introducing the delta function of that auxiliary function f. So by taking the derivative of this flux with respect to time, delta t, we'll obtain the transition rate, which is number of transitions per unit time. And this is what you get by implementing all these results here. And this looks like a horrible expression, which is very difficult to use in practice. It can be used in practice, actually, but it looks rather complicated. We will work out an analytical expression out of this one using a certain number of approximations now. First of all, one can notice that integration over the velocities can be performed analytically. And this is because the distribution over the velocities is Maxwellian in the Gibbs distribution, and that's why this can be done. So the idea, very briefly, is this. So we have velocity integration in the numerator and denominator. Okay, so in the numerator, we have this dot product of the multidimensional vector of velocities and the gradient to the dividing surface, which for the integration of the velocity is a fixed vector for the given q. We also have this Heaviside function, and then the exponential of the kinetic energy. Exponential of the kinetic energy. Kinetic energy is a sum of atomic velocities. But in fact, one can actually introduce new velocities, massless velocities, and then that kinetic energy would be simply v square, where v tilde is the new vector of massless velocities. And then the whole integration can be performed by rotating the system, so in the v space. I don't know if I need to go through the details, maybe it is not that important, but that integration over the velocities can actually be performed. And if you do this integration, you will obtain this result when this EQ is this vector. It's related to the normal of our auxiliary function, the normal to the dividing surface. And the same can be done for the denominator of that transition state theory expression. This calculation is much simpler. And in the end, you obtain something like that. So here we have got rid of velocity integrations altogether and only have integration over the space of our coordinates q. So in the numerator, we have a surface integral over the dividing surface, and in the denominator, we have an integration over the reactant basin. Again, it looks like a very complicated expression, but in the harmonic transition state theory, this expression can be actually worked out explicitly analytically. And again, a few words on how this can be done. So if we are in the reactant basin, our initial state, we can assume that it's given by the harmonic potential. So this is a harmonic energy. This phi is a force constant matrix as measured at the minimum of our reactant basin, basically here, the minimum of our reactant basin. It's a quadratic function of the displacements of my system from the equilibrium position Q naught. And by using massless displacements, y, it can be worked out into this quadratic form, as we did several times before. And therefore, the integration in the denominator, this one here, can be performed as we did before for multidimensional Gaussian. It can be actually integrated, and you get this result. The calculation is performed by going into normal coordinates, and then after all this calculation, which is not really difficult, but I don't think it's appropriate now to go into much detail, but you have basically product of independent Gaussians when you go to the normal mode. You obtain something like that. It contains velocities, which is not velocity, frequencies of our system in the basin, reactant basin, where the system is initially in the minimum. So this was denominator. What about numerator here in the transition rate? Here we need to integrate over the reactant basin or reactant dividing surface. How shall we do this? First of all, this is a saddle. Remember, I was telling you that if you go along the dividing surface, the energy goes like this, and here is the point where we have a minimum. However, if we deviate from the dividing surface to the left or to the right, towards one minimum or the other, the energy goes down. So it's like a saddle. Yeah. So what we should do then? Here we can also use the transition, the harmonic approximation, but this time we will write this expression for the potential energy around that saddle point, which is called transition state. It will contain the energy at that point plus quadratic terms associated with displacements out of this point, and there will be a few terms there. First of all, there will be terms with the positive coefficients. This corresponds to atomic vibrations within the dividing surface. They will have omega squares frequencies positive, but there will be 1 degree of freedom, precisely 1, which corresponds to displacements out of the dividing surface, and that will come with a minus sign. This omega square would contain this minus sign in front, which of course is what you would expect, because that point is a singularity. It's an unstable point. There will be 1 imaginary frequency in this case, and 3 and minus 1 positive frequencies, real frequencies. Then you can work out other terms which are required for the calculation, and then you would need to integrate over the dividing surface. And when you integrate over the dividing surface, you integrate over all degrees of freedom within the dividing surface, but you're ignoring that single degree of freedom which taken you out of the dividing surface, which corresponds to the actual transition. So you integrate over all but 1, and this is denoted by this prime. And if you perform this integration, you obtain this result, which contains now vibration frequencies only within the dividing surface. That is denoted by this prime here. Dividing this result by our previous result for the denominator, we obtain the final expression due to Vineyard, 1957, this reference for you, which shows that the transition rate is given by the following. First of all, there is an exponential term, and here in the exponent we have the barrier. So you see, we have the potential energy at the transition state minus the potential energy at the minimum of the barrier. So this is precisely that energy taken from here and here. So this is the energy barrier, exactly the same as in the one-dimensional case. But there's a prefactor here, and the prefactor is very interesting. So what does it have? In the numerator, we have a product of all vibrational frequencies at the minimum of the reactant basin. In the denominator, we have all the vibrational frequencies at the saddle point here, but 1. So all frequencies, but 1. The one which is imaginary and corresponds to the actual transition is not here. You can assume, for instance, that at that point only 1 frequency changes. So you can imagine that as you go down to the reactant basin, all these frequencies corresponding to the reactant to the dividing surface remain the same, but the frequency which takes you to the transition, that changes. Initially, when you're in a basin, the frequency is positive, but as you approach reactant saddle point, that frequency becomes purely imaginary, and you do not account for it here. Okay, so if we assume that all other frequencies but this one do not change as you go from the minimum of the reactant basin towards the saddle point, they will cancel out. So 3 and minus 1 frequencies would cancel out, but that product contains 1 frequency more. And that's the frequency which doesn't cancel out. It's a frequency along the transition but from the basing. So we have here that omega divided by 2 pi times the exponential, and this is exactly the one-dimensional result, where omega naught divided by 2 pi also present, and omega naught is precisely the vibrational frequency in the basin which takes you towards the transition. So what is the lesson here? If you really want to study kinetics and you would like to study how the system evolves in time, jumping from one potential energy minimum into the other, you will need to calculate these rates. For example, if you're using kinetic Monte Carlo methods, then of course the first thing you would do is to use natural elastic band method to calculate the barriers, so to localize the transition state, the saddle point between two minima, and work out the energy barrier. But if you would like to be more precise, you would also need the prefactor. That prefactor can be calculated by calculating vibrations in the minimum of your potential energy, of your reactant basin, initial state, and at the saddle point, where you will find one vibration imaginary. This is not very easy to do because you need to localize this transition state and the minimum very, very precisely. Otherwise, you will get more than one imaginary frequency. But in some cases, this calculation can be done ab initio, and this way you will get access to the prefactor as well. So that's basically all I want to tell you. We have about 10 minutes for questions. Of course, this is just an overview. If you are interested in this, you will have to study this yourself, but I hope I gave you kind of a general picture for all these different developments. Any questions? Please do ask. Have you found it useful at all? Oh, there's something in the chat. Let me see. Okay, so somebody said it's useful. That's good. Maybe another vote, if you don't mind. Have you found this difficult, this material difficult, challenging? Because I don't know what the level of other lectures is. Have you found this kind of mathematically challenging or okay-ish? All right, anyway, I think we're done. Densely packed. Okay, yes, but you will have your slides, you have your videos, so you will be able to go at your own pace now again through this. Okay, thank you very much for your feedback, and bye-bye.